Okay, so we are continuing with Prony's method, and let me erase this part. Okay. So let's focus on the special case of this. So this is the general case. This is called, as you can imagine, we are paying special attention to this, all-pole modeling. Okay. So this is a special case of this general case. So what do I mean by this special case? H of z is equal to B0, 1 plus AP of 1, Z inverse, AP of 2, Z inverse to the power 2, plus some other terms and the last one. So what do we have? We have number of zeros is equal to 0, because we have only B0, constant term. Number of poles is equal to P. It's a little strange looking, but P is equal to P. Pole is equal to P. So degrees of freedom is, well, this is P plus 1 degrees of freedom. Degrees of freedom. So what's degrees of freedom? Number of coefficients that I can select, such as this one, freely. Okay. Now this is the general case. So as you see, I have, on the numerator, it's a possibility of having q poles. Okay. But I have only 0, as you see over here. So this one is equal to, an unknown. So this is B0 in my case. And the other ones, they're just absent. They're all equal to 0. Okay. So if that is the situation, then, so let me write this Prony error. J Prony, I was writing this Prony over here, of this AP vector. Let's do not make a mistake. Prony error is equal to, n is equal to, in general, q plus 1 to infinity e of n magnitude square. Okay? That is a general Prony error. But over here, q is equal to 0. So this is equal to, n is equal to 1 to infinity e of n parenthesis magnitude square. Okay? Well, the reason is, now this red line is, as you see, this is the separation of the upper part and the bottom part of this matrix. We have discussed this bottom part in length. Now, this red line is moving to this first, just after this first row, because q is equal to 0. Okay? So how about this? Well, note that E0 is equal to, E0 is equal to what? N is equal to 0, error at N is equal to 0. Left hand side minus right hand side is equal to x0. This is correct. Minus, let me see, B, well, B0, that is it. Because I have only this one, B0. Therefore, then, quick note that this is not a function of AP of case. So clearly, there are no A's affecting this. So how about this? Let me change this Prony error. This summation index, now it starts from 0 to infinity. Let's say with hat. It's different from the earlier one. But what is different is, the summation index starting from 0, okay? Instead of starting from 1. Because the red line was moved to this, and I was talking about the bottom part of this matrix. But you can see that this error at 0 is not a function of A. So this is, if I take a derivative with respect to this APs, those derivatives will be with respect to AP will be equal to 0. So this is just a constant term, okay? For the sake of this function in terms of A. This does not depend on y. So I can add this constant term to this one, E0 magnitude square. Then the summation, lower part of the summation, lower index will be starting from 0. Then J hat Prony of this vector has the same optimal AP vector of J without hat, Prony AP. Because all the differences E0 magnitude square term, this is just a constant term for the sake of optimization. Now if I have that, then, let me keep this, let me erase this. Okay, let me repair this part. Okay. Now we have, for this calculation, Rx, K, L. We have defined this. N is equal to, again, from Q plus 1, we should calculate it like this. X, N minus L, X conjugate, N minus K. This is for this calculation. Okay? Let me see, is it the case? It's exactly like that. But for this, let's say, summation, so only thing that is different is, as you can imagine, this summation is not starting from Q plus 1, but it's starting from 0. So I will be changing this for the sake of all pole modeling. All of these calculations are the same. So the summation index starts from 0. Okay? That is the thing that is only changed because, previously it was Q plus 1 and we have derived these equations, and I don't want to derive them again and again because it's the same calculation, only the lower index of the summation is different. Okay? So then this is valid. Okay. But how about this? There's something else going on also. Rx. So first of all, what is this K in this calculation? K, as you can see, one of those unknown, these ones, indexes of one of those unknowns. It ranges from 1 to L, 1 to P. So K is an element of, integer in between 1 to P. Okay? So how about L? So what is that L? You can see that that L is also in 1 to P. Maybe I shouldn't write this, but element of 1 P, okay? Because it's integer. So this is 1 entries, KL entry. So those are the entries that I need. So how about this? Rx, K plus delta, L plus delta. For example, if I know this, well, if I add 1 to this one, delta is equal to 1. 1, 2 becomes 2, 3 if delta is equal to 1. Okay, so I'm looking at this kind of a diagonal terms. So about this one, again, delta is an integer, obviously. It's a positive integer. Okay. Delta integer. Then this becomes n is equal to 0. Infinity x n minus L minus delta x n minus k minus delta. Am I right? Because that is the way it is. Okay. So what should I do? So instead of k, I'm writing k plus delta over here. L, that is it. So let me then change this summation index. Let me increment the argument of this summation by delta. So this is, let me write f. There are n's, fn. These are all constant for the sake of this summation. So I'm adding only fn's from 0 to infinity, f0 plus f1 plus this. So about doing this, I'm writing fn plus delta, but n is starting from minus delta to infinity. So do you see that the end result of these two summations are the same? Obviously the same if you check it term by term. So this becomes f0, this becomes f1, and so on. So f0, f1, and so on. So if I do this, so incrementing the argument by delta, decrementing this, indexes by delta, decrementing indexes by delta results in the same terms, obviously. This is actual change of variables, but it's a faster way of doing things. Okay, so I'm incrementing this, n minus L, n minus K. There's a conjugate somewhere. Okay. So I have managed to cancel this, but as you see, this is starting from minus delta right now. Okay, that was expected. But what do we know? Well, here is the case. If you check this, this is starting from, let's say delta is equal to 5. So this is starting from minus 5, minus 4, minus 3, and so on. But L and K, they are also, integers like this, 1 to p. And we know that, do you remember? Unfortunately, I have erased that part. X of n, at the beginning of this, is a given sequence. Something like this. This is still the same problem. But for negative n indices, x of n is equal to 0. Okay. So for example, n is equal to minus delta. N is equal to minus delta, this is a negative number. Minus L is a negative number. So this is 0. Because argument of this is equal to 0. So you can see that this is, okay, minus delta, but, okay. I will be starting this summation from 0 to infinity, x n minus L, x conjugate n minus K. Okay? Because I am sure that when n is equal to 0, let's say n is equal to minus 1, let's say. When n is equal to minus 1, I am sure that this term will be equal to 0. Or the other one will be equal to 0. I'm sure about it. So for all of those terms ranging from minus 1 to minus delta, they're all equal to 0. So I'm not sure what will happen at, n is equal to 0, but, well, that is the case. I'm starting from n is equal to 0 because of my previous definition. Actually, I know that this is also equal to 0. But this is equal to Rx, K, comma L, as you see. So what do we see? If I compare this, well, we see that we see the following. Then Rx, K, comma L is a function of K minus L. Okay? Because if I increment both of these arguments by delta, then I get the same thing. So in other words, I can write Rx of, well, let's say K minus L. It's some abuse of notation. 0 to infinity. X n minus L. X conjugate n minus K. Because it doesn't matter. So I'm, instead of KL, I can write this K minus L. Because I'll be getting the same thing for let me see. When L is equal to, for example, when delta is equal to minus L, so this becomes Rx K minus L. Okay? And at the zeroth leg. So let me define something like that. Okay? This is my new definition. So with this new definition, so I'll be rewriting this matrix. So this becomes Rx of 0. This becomes Rx of minus 1. This becomes Rx of minus, is it P minus 1. So I'm rewriting this matrix. So this is Rx of 1. So is this familiar to you? Well, this is almost like the same matrix that we have seen. Is it Rx of P minus 1, Rx of P minus 2, Rx of 0. Okay. I have such a case. And this is AP of 1, AP of P. So I'm writing this matrix one more time. Is equal to Rx of 1, Rx of 2, and Rx of P. I have such a case. Let me see. This is 75, Rx 0, function k minus L, so this is the differences k minus L. I think it's correct. So we have such a case. So what do we see? This is almost like, okay, that's all the same. So this is, please compare this equation set, this equation system with autoregressive ARP process, let's say ARP process. This is Yule-Walker equations. Okay, Yule-Walker equations. So only difference is that those R's were the expected value. It were calculated according to the expected value results. Okay, but this one is deterministic autocorrelation. Okay, so this one is, let me write Rx of, let's say gamma for this one. N is equal to 0 to infinity. X of n, x conjugate n minus, let's say gamma over here. So over here, this is, let me maybe do one more step. So the difference is k minus L, the second conjugated argument is subtracted. So, well, T1 minus T2, okay? So this is time 1, T2. So this is T1 minus T2, okay? We have a case like that. So similarly, time 1 minus T2. So this is exactly the same. Okay, so how do I get this one from this one? Again, increment the argument of this sum by L, then this becomes this. Decrement by minus L, but all of these minus L indices are equal to 0. You can again get this immediately. Increment this argument of this summation by L, meaning that this is instead of n, I'm writing n plus L. Then this becomes n plus L minus L, n. So this becomes L, this is n plus L minus k, okay? So I get this again. Once you do that increment, then you need to decrement this summation index by minus L, by L. But like this discussion, all of these negative indices, because the x of n starts from 0, all of the previous entries with negative index are equal to 0, then you'll see that even though this starts from minus L, I can start this summation from 0 because all the negative indices contribute a 0 to this summation. Okay? So this definition and this definition are the same. Well, That is the way it is. Okay. Now, almost like the Yule-Walker equation, only difference is this is what we call a deterministic autocorrelation. So, this is the connection between stochastic modeling for the AR processes and deterministic modeling for the all-pole, let's say, transfer functions. Okay. So we have such a case. So what is important for our purposes is just, the solution of this. But in practice, assume that you are doing a stochastic modeling. Nobody in practice is giving you the, autocorrelation of a sequence, random process. Autocorrelation sequence is not provided in general. So you estimate this autocorrelation process. So in general, you are given the samples of a random process, like x of n. This is the way you estimate the autocorrelations, let's say estimate for the autocorrelation sequence. Okay, this is one way of calculating it. Then once you calculate that, you insert it over here. Then the stochastic problem becomes exactly like the deterministic problem. Okay? So let me rewrite this maybe in a sentence so that it would be perhaps useful. In practice, ARP process synthesis, okay, that is generation of H of Z filter generating ARP process with a desired, let's say, power spectral density requires autocorrelation, I think it's clear, Rx of K, which is autocorrelation. Let me write this because there are too many autocorrelations. Expected value of x of n minus k conjugate. Okay, obviously because we are working with the stochastic problem. Now, if this is needed, but requires, but Rx of k is only estimated by, sometimes you have more information, but it's only estimated by this. Conjugate. So this is deterministic autocorrelation. Okay. I'm erasing this matrix, I think it's clear. So what is this x of n? So this is x of n is observed realization for a random process, for the random process. So in practice, you observe something about this random process. Then you say that, well, I need to produce a filter generating that random process. So this is, of course, you need the autocorrelations. Nobody is giving you the autocorrelations. So you estimate the autocorrelations. Let me put, if you wish, a head over here to denote that this is different from this one. But this is the estimate of this one in general. There can be a normalization over here, like 1 over n and so on. But this is, okay, details. Okay, then what happens? If you insert this, then using Rx hat of k instead of the true values Rx of k in Yule-Walker equations, results in a problem identical to, results, not a problem, results in a solution results in a solution identical to the one for all pole AR modeling, or not AR, all pole modeling with Prony's method. So as you see, you are trying to do maybe different things, but the result is the same, because all of these intermediate calculations, they converge to the same result, and once you insert it, you get exactly the same equation system. Okay, so that is the end of this modeling discussion. But there is one more, a short topic, which is, should I erase this? Let me also erase this. So that is the end actually for, deterministic modeling, but let me do one more thing. Should I erase that one? Let me erase that one also. Okay, so we are almost done. So let me see. All pole modeling, a brief topic, but practically important, with finite data records. The data records. So up to now, we have assumed that x of n, we have assumed that x of n, this is a measurement or observation, is given in for, let's say, n 0 to infinity. Again, in practice, x of n is known, this is the measurement, for n is, let's say, 0 up to capital N. Okay? So please remember, this is my x of n sequence. This is, let's say, a measurement, and I'm trying to fit an all pole system to this measurement, x of n measurement, but it's not right now extending to infinity, but I have only maybe n samples over here. So I don't know what happens anything after this, n samples. So how should we take into account this knowledge? Now I don't have infinitely many x of n's, but only n samples. So how can I take into account? So for finite data records, meaning that this n is finite, this n is finite, okay. We have two methods. Number one, this is called autocorrelation method. Okay. So we are using this matrix as it is. We use, let me see, this matrix system. We use the matrix system as it is in Prony's method with no changes. Okay, with no changes. So what does it mean? Now let's assume that I have my last sample is x of n. So I don't know what happens afterwards. Then in this matrix equation system, this starts from x0, it goes to x of n. So this is the convolution matrix one more time. So this is the shifted version of this, x of n, 0, 0, x0, x of n. Okay? So this goes like that. Okay. So I have these, again, 1, AP1, AP of P. So my unknown is, because it's all pole modeling, there are number of zeros is equal to 0. So this is 0. The rest is all of, this goes to 0. Okay. So in the autocorrelation method, now we assume that we use this as it is, but we do not know this xn plus 1 over here. So we just say that it's equal to 0. Okay. Okay. It's all equal to 0. So as you can see over here, xn plus 1 is taken as 0. So in the autocorrelation method, we use this matrix as it is and fill in the entries that we have no measurement with zeros. We fill all entries without measurement with a 0. So you can say that I don't agree with this with a 0. Because, you know, we have no idea about that entry, but so in practice, because if n is a very long, a very large number, if it's a very long vector, then you expect that impulse response should die, isn't it? Die out at the end. Okay? So if n is very large, maybe this 0 assumption is not very bad. But if n is very small, then you suddenly cut and truncate this impulse response or the measurement. So for finite data records, the problem becomes tricky if this finite record is of small sample size, let's say, if it's very small, n is very small. So this may be not a good idea because you are suddenly truncating the measurement and inserting a 0 afterwards. Okay, this is called the autocorrelation method. We apply this, we fill the unknown entries with 0 and apply the usual, let's say the equations, the usual solution. Okay? Apply the usual solution. So I'm filling the matrix entries which are unknown to me with 0 and then apply the usual solution with, meaning that Prony's method that we have previously explained, like this was Rx of 0, Rx of minus 1, and so on. Rx of minus p plus 1. The matrix that I have erased, okay? AP of 1, AP of p. So this is the same thing that we have previously said about it. So only thing that is new is this introduced zeros. Okay, you may object to this, especially when it is not large enough. Then there is a second method. The names are a little bit confusing, but this is the way it is in the literature, unfortunately. This is called autocorrelation method, and maybe this is good. For this one, it is good to call this autocorrelation method because, let me write it over here, Rx of, please remember, gamma is defined as so indeed this is autocorrelation, isn't it? This is our autocorrelation, deterministic autocorrelation, and this is valid for this one. Only difference is zeros are substituted whenever I need them. Okay? That is it. So this is the reason maybe it's called autocorrelation method. Now the second method is, this is called covariance method. For finite data record. In the covariance method, we don't want to introduce any assumption into the equation system. Okay? So let me see. I think we have a battery problem over here. Okay, let me turn this. Out. I hope it is fine. Okay? I hope you can hear me. So for the covariance methods, then we don't want to introduce any assumptions. Okay? We don't want to introduce any assumptions regarding this. Then, no assumptions for x of n, okay, values which are not observed. Okay? There are no assumptions on that. So how can I have that? Well, that is the case. So in this matrix, let me look at this. if I have for the covariance method, this is x0, 0. x1, x0, this is 0, this is xp minus 1, xp minus 2, x0. And this is x of n, x of n minus 1, n minus p. So what is this matrix? Well, as I have said, for all pole modeling, we are moving this red line over here. Because q is equal to 0, and q plus 1, starting from q plus 1, I have zeros all over here. Now, the first column is multiplied by 1. Let's move the first column to the right. 1, 2, goes like this. Okay? I have things like that. Then, this one. The second column is multiplied by AP1. So this is the second column of this big matrix. But these are the values that I observe. So these are the values of multiplied by AP2 and so on. I think it's clear. Okay. So for this one, is this clear? I have such a case. N minus 1. So over here, what do I observe? I have only samples up to x of n. So covariance method uses this part of this matrix. Okay, this part of this matrix. Well, I should maybe write a correction over here. X of n, x of n minus 1, x of n minus 2, x of n minus p, this is minus 1. Okay. So covariance methods uses in equation solving only this part of this matrix. I'll write this a little better. X of p, x of n, I have this green dot, and this is x of n plus 1. Okay? So what is special with this green part? Covariance methods, submatrix, covariance methods, submatrix. So you see that in this part of this matrix, I have no assumptions on the data. I have no assumptions. Previously, for the negative entries, it was also assumed to be 0. Well, it makes sense for, causal systems and so on, but maybe we don't want to assume that also. Okay? Maybe this is not an impulse response, but some other measurement that you are trying to fit something. Then, for all pole modeling, as you see, now I have an equation system. This middle part of this matrix times this vector is equal to another vector. So this covariance method only uses this part of this equation system and applies the least square solution to that part. Okay? Okay, so covariance methods applies least square solution submatrix to the how should I write? To the submatrix, let's say. Submatrix system of equations between green dotted lines. Green dotted lines. Okay? So forget about the rest. Covariance method says that, okay, my first equation is this, observation vector, inner product with this is equal to something. Last equation is this, inner product with this equal to something else. Okay. So it does not make any assumptions. You may think that, okay, this is better because it has higher fidelity to data. Fidelity means you are not making or introducing any arbitrary assumptions into the equations without any justification. Okay, that's good. So here are some comments. For finite data records, for let's say when n is small, covariance method, this is not a certainty, can perform better because it's not making this arbitrary assumption about these unknown entries of the observation. Can perform better. But it's just a can, we don't know. Okay? You should give it a try. Number 2, autocorrelation methods. Now, surprising things can happen. Is guaranteed to give a stable filter as H of C model. Okay? Please remember, we were trying to give a stable H of C because this looks a little strange. A stable H of Z system. Well, I'm not proving this, but this can be proved. Also, I think the proof exists in Hayes's textbook. So it's a little surprising. Autocorrelation method, even though it's introducing those zeros in an arbitrary manner, it is doing something good. The estimate H of C is always guaranteed to be a stable system. Actually, it's quite a relief in system design, isn't it? Because at the end of the day, now you are sure that if you apply this autocorrelation method, your model, at least it's not divergent, okay? You have meaningful model maybe, okay? We have that. What else? Let me see. There is a third one. The matrix, well, this is just a detail. The matrix for, let's say, autocorrelation methods. Method that is this x times 1 AP is equal to B0 and 0. This equation system, X matrix with filled in zeros. Okay, this is this. Results in X transpose X being this, okay, being positive definite. Positive, we say semi-definite. Actually, it's positive definite. This is just a detail, but now we will be taking the inverse of this. Okay? Because please remember, in this calculation, we had this, okay, there are these details, bottom part, rest, bottom part, rest. This is transpose, isn't it? We had inverse, well, part rest transpose. This is x1. There was a minus sign somewhere. Okay. So this is the matrix that I'm talking about. So this matrix becomes positive definite. Well, it's not very surprising because I'm using this whole matrix. And you can say that this column, this column, this column, they're all linearly independent from each other. Okay. So this matrix becomes, full rank, full column rank. Okay, full column rank. Of course, it's full rank also because of that. Then I have an invertible x transpose x. Okay. So that is the way it is. That's all I would like to say about autocorrelation method and covariance method. This may seem like a little bit of a detail, and names are a little confusing. Why this is called covariance and why the other one is called autocorrelation, and so on. But that is the way it is in the literature. That is the way it is established in the literature. And these are very practical things. In many applications, you may have to do such a modeling of a given observation. You observe such things, and you are trying to construct a model. Well, you can say this is like a compression problem. Now, instead of keeping this, you are just keeping maybe this many coefficients, especially in speech processing and so on. This is very important because this is maybe a long speech frame with, 1,000 samples. Okay? But if you can generate these samples by a model excited by a white noise, let's say, and this model corresponds to an all-pole filter with filter coefficients, something like that, related with this, then we are only keeping these p coefficients. Okay? And if it can generate such output, then it becomes like a compression issue. Instead of storing this, if I can represent them good enough with these p coefficients, then this becomes a good model for our purposes. So for the deterministic modeling, please remember, I'm just inserting a delta. I am trying to estimate, let's say in this case, an AR, all pole, okay, AR, such that this H of n is almost like X of n. Okay? So if you can identify such a system good enough, coefficients of keeping that system, coefficients of this system totally determines this output, which is X of n sequence. That's what I'm trying to say. Okay, now we are done. So I'm erasing this big matrix finally. Previously, I have said something about complex optimization taking derivatives with conjugates. I would like to briefly talk about that, and that will be the end of this hour. So let's say optimization with, let's say, complex variables. Okay. So one thing is, well, we have this concept of cost function. Let's say that this is, Z is a complex variable, X plus JY. Okay? So this is, say, function of a complex variable. Complex variable Z. Okay? Now, there can be issues. There is, for example, J of Z. It can be written as Z elements of complex numbers 2, or this can be from complex numbers to real numbers. Okay? Well, that is the case actually that makes sense for a cost function. So what do I mean by that? For example, we may have two complex variables. Then we define something like this: Z1, Z2. There's a matrix A. Z1 conjugate, Z2 conjugate. Let me have a simpler thing. Z1 minus 1 minus J magnitude square plus Z2 magnitude square. Okay. Well, this is a trivial optimization problem, but you see that these are complex numbers. So this J is from Cartesian product of complex numbers to real numbers, because at the range of this function, I have a real quantity. So this is the magnitude square of this complex number. Okay. So for such functions, optimization makes sense. So these functions are called, for such functions, for example, this one, J, Z1, Z1, Z2 is a complex, is a function of two complex variables. Is a, let me write, real valued function of two complex variables. Okay? So this real valued function. Okay? Real valued function is in the range of this function, this part, I have real values. So this can be different. This can be matrix valued function of two complex variables. Okay? Maybe I'm just multiplying these quantities by matrix 1, matrix 2. Okay? Then these, at the end, you have matrices. Okay? So this can be a matrix valued function. On the range of that function, you have matrices at that time. Now, if this is the case, now you want to optimize this. If real valued function of two complex variables is the cost function. Oh, let me write a note. Note, complex numbers, obvious, but cannot be ordered or compared. In other words, you cannot say that 1 plus j is greater than 3j over 5. Okay? This doesn't make any sense. Complex numbers cannot be ordered like that. There is no ordering like that. But this makes sense. 1 plus j in magnitude greater than 3 over 5j. Okay? This is okay. Because at the end, you have a real number over here, and real numbers can be ordered. So this is square root of 2, for example. This is, magnitude of this complex number. This is 0.6. Square root of 2 is greater than 0.6. But complex numbers cannot be compared or ordered like that. So if you want to minimize, such a function, a real valued function of two complex, this makes sense because you are minimizing real values. So you can, you find a minimum, meaning that you are finding the smallest value at the range of this function. Smallest means I'm doing the comparison, and that is the smallest value. Okay? So that is the case. Now, I think this is good enough. So let me work with that. Z1, Z2. This is Z1 minus, let's say, 1 plus j. This. So how do you minimize this? Well, the minima is obvious. If Z1 is equal to this, and Z2 is equal to 0, this is 0 plus 0, I have 0. That is the minima, but how can I find that? Well, let me call this Z naught for the sake of simplicity. So I can write this as Z1 minus, let me call this W. Z1 minus W conjugate plus Z2 conjugate. Do you agree? Because this is magnitude square of complex numbers. Now I will be taking derivative with respect to Z1 conjugate. Okay, let's give this a try. Now, and equate it to 0. If you take the derivative with respect to Z1 conjugate, now you have Z1 conjugate over here, multiplies this. So you treat Z1 as an independent variable. Okay? So I'm taking this, okay, this term. So this is equal to Z1 minus W. Okay? So I'm using this over here. Now, this derivative result becomes Z1 minus W. Derivative of Z1 conjugate with respect to Z1 conjugate is equal to 1, is equal to 0. Then you say Z1 is equal to W. Okay, this is the optimality condition. I'm doing this. So the other one is even easier. J Z2 conjugate is equal to 0. So I'm differentiating with respect to the other one. Z2 is equal to 0. So these are two independent variables according to this calculation. Then you have Z2 is equal to 0. Okay, indeed. When Z1 is equal to 0, this is 0, this is 0, 0 magnitude square is 0, this is 0, 0. So this is the solution. Now you may wonder, well, okay, how is this possible? Because we have said that Z1 has a real part and imaginary part, so this has 2 degrees of freedom. Z2 has 2 degrees of freedom, so I should have a 4 degree of freedom at the end, but I'm taking derivative with respect to only 2 of them. Well, the issue is this. The critical observation is this. If you take the derivative of this with respect to Z1 and equate to 0, so you get the conjugate of this, whatever you have, this is your first equation, let's say. So you get the first equation's conjugate is equal to 0. Okay, so this is, let's say, 1. So it's very obvious again for this one. If you take this Z1, you get this one's conjugate is equal to 0. Okay. Then for this one, if you take the derivative with respect to Z2 and equate it to 0, so over here, let's say this is the second left-hand side, 2. If you do this operation, you have 2, whatever you have on the left side, conjugate is equal to 0. Then, well, if you only know 1 is equal to 0, then automatically 1 conjugate, this is 1 conjugate. If you satisfy this, this is automatically satisfied because this is 1, Roman numeral 1 is equal to 0. Roman numeral number 1 conjugate is also equal to 0 because 0 conjugate is equal to 0. So similarly, Roman numeral number 2 is equal to 0 if you can satisfy this. Then this conjugate is also equal to 0. So you see that it's a little confusing. This requires some proof and so on. But just calculating this and this, working with only 2 degrees of freedom, guarantees that third and the fourth degree of freedom is also at the optimal value. Okay. So this is the reason that we prefer to take derivative with respect to Z1 conjugate, or doesn't matter with respect to Z1, instead of taking derivatives with real part of Z1 and imaginary part of Z1. If you take real and imaginary parts of Z1 and Z2, you have to calculate 4 derivatives. Instead of 4 derivatives, you are calculating only 2 extremely simple this time derivatives. Okay? But again, this is all valid for when this function is a real valued function of complex variables. Okay? So I have prepared some lecture notes some time ago on this, if you are interested, for exactly for this purpose, to explain this. Let me see. This is, okay, please check this if you're interested. Title is Properly Handling Complex Differentiation. This is this operation. In, let me see, optimization and approximation problems in optimization and approximation problems. Let me see. This has appeared in IEEE Signal Processing Magazine. Signal Processing Magazine. Lecture notes. Column. March 2019 issue. Okay, March 2019. So if you are interested in this topic, this optimization with respect to this complex variables, please see this. I couldn't write it very well, but IEEE Signal Processing Magazine Lecture Notes kalın. March 2019 issue. Okay, that's all for today. So we will continue with more discussions at a later time.